What's going on? It's Brandon Styles, and today we are going over an Amazon coding problem. It's called Path Sum 2. Now this is one of the medium hard problems in Leetcode, and I wanted to walk you through it as best I could and kind of show you how I think about a coding algorithm problem. This one is particularly a depth first search problem on a binary tree. Now if that doesn't make sense, I'm going to try and show it to you and explain it as best I can. So let's jump into the code. All right, so here's the problem we're looking at today. It's Leetcode question number 113, Path Sum 2. Now this question is being asked by companies like Amazon. And it says, given a binary tree and a sum, so here's our binary tree, and the sum in this case is 22. Find all root to leaf paths where each path's sum equals the given sum. Note, a leaf is a node with no children. Okay, so essentially what we want to do is we want to start at a root. In this case, in this example, the root is going to be 5. And we want to go all the way to the bottom. So 5, 8, and 13. 13 works because it's got no other leaf nodes. Or 5, 8, 4, and 5, right? 5 has no other children, 1, things like that. And we want to see if any of these paths add up to 22. So does 5, 8, and 13? Does 5, 8, 4, and 1? 5, 4, 11, and 2? So on and so forth. And we want to return an array of arrays, right? Here's an array, and then here's another array, and this one has 5, 4, 11, and 2. Add those together, you get 22, and you also get 5, 4, 11, and 2. This works out because there's no children right here. So how do you do this? Well, when I'm looking at a problem like this, and anytime you're kind of traversing a tree, most of the time when you're traversing a tree, and this is essentially what this is, I'm thinking a depth first search, and I'm thinking a recursive function, meaning you just kind of fold the function in on itself over and over and over again, and if you try and figure it out on paper, it's kind of a mind screw. But this is how I think of it, and this is how I do it. So anytime I'm preparing for one of these problems, I plan out 4 steps, and the steps go like this. Number 1, you want to do some basic error checking. All right, make sure you have a root, make sure you have a sum, anything else you want to do. The second step, I want to create any variables that you'll need. All right, and we'll look at that in a second. The third step, we want to call the magic function that gives us an answer. So what this means, and I stole this from Kevin Naughton Jr., who has a really good programming and algorithm solving YouTube channel, so check it out. What this does is, if you didn't know code, but you knew that you could just call a function to solve this, you would put that right here. So if it could be called Pathfinder, and you could just put Pathfinder right here. And the trick is to kind of create a shell function so that you can kind of build that function on its own and don't have to worry about error checking, variables, and what you're returning, all right? It made a lot of sense to me, so hopefully it makes sense to you. Step 4 is you actually have to write the magic function. And then the final step is you just have to return the answer that's asked for. So in this case, it wants us to return an array of arrays, and you can call that whatever you want. So return, just for right now, as a placeholder, the answer. So this 5-step process will solve a lot of questions. Do some basic error checking, because companies you're interviewing with are going to want to see that. Create any variables you'll need, so will you need to hold the place of something, will you need to keep track of a counter, etc., etc. Call the magic function that gives us the answer, so in this case we'll call something called find paths or whatever. Then you need to write that function, and then you need to return the answer that's asked for, in which case it says find all paths, essentially right here, find all paths. So let's get into writing this. So we know from these instructions up here that we are going to be giving a root that's on a tree, and that each root or each node on this tree is going to have 3 properties. It's going to have a value, so in this case it would be 5. It's going to have a left value, so root.left in this case would be 4. And then it's going to have a .right value, so in this case root.right would be 8. So that's what we know going into it. Now let's actually solve this thing. So first let's do some basic error checking. So I want to make sure there is a root and there is a sum. All right, so I'm going to write if there's no root or there's no sum, return false, right? There's no point in even doing the problem using computational power. Now the next one, if the sum that we're given is smaller than the root, this problem is not going to work anyways, right? If the root is 24, but the sum is 12, the problem can't be solved. So I'm going to say this. If root is greater than sum, then we also want to return false. There's no point in even going on with the problem because it's unsolvable. Let's give a little bit of space here. So now that we've got some basic error checking done, we want to create the variables that we're going to need. So usually in a depth first search recursion problem like this, we're going to want to store the paths, right? We need to traverse each path So we need to go 5, 4, 11, and 2, let's say. So we need to keep track of that somehow, especially if it's the right one. So I'm going to create something called const paths that add up to sum equals a blank array. Now remember, this is going to be our final solution. So this is what we're going to return. The next thing is we want to keep track of the current path being explored. So if we're doing our recursive search and we're on 5, 8, and 13, we want to store that somewhere so that we can check against the sum. Or if we're on 5, 8, 4, 1, we want to store that somewhere so we can check it against the sum as well. So I'm going to call this current path being explored, and it's a blank array. Now this is going to store the result of each recursive pass. So if we're on the 5, 8, 13 strand right here, it's going to store it in this array. If we're on the 5, 8, 4, 1 path, it's going to store that, 5, 4, 11, 2, so on and so forth. So now we've created the variables that we will need. So now let's call this magic function that we have not written yet. And since we're just finding paths, I'm going to call it find paths. And then we're going to be passing it the root, right? We need to know where we're starting. In this case, it's a 5. So if this were just a hard-coded problem, you would pass 5 in. And then we want to know the paths that add up to the sum. We need access to that in this method. And then we also need to know the current paths being explored so that we can keep track of what path we're on. And we also need the sum, in which case is 22. So we would put 22 right here. So that's how our recursive function, if it were hard-coded, would look. Now we don't want this to be hard-coded, so instead of 5, we're going to write root, and instead of 22, we're going to write sum. And so there we go. So now we have called this function. We've returned the paths that add up to the sum, which are going to be stored in this array. So it's going to return this number right here. And that's it. So all that's left is to write this magical function. So let's just start by creating it. So I'm going to write function, find paths, and then again, we want to pass it all this stuff right here. So the root, the sum, the paths, the current paths being explored, blah, blah, blah. And then we're going to pass this into a function right here. And then there's the end of the function. Let's open it up. And now let's get to coding. So the first thing we want to check, like let's say we're on 5. Let's just use the example of 5. So if we didn't have a root here, we want to return out of this function and go back to the main thread. This is the main thread right here coming down this side. So anything that's inside, indented in this function, is outside of our main thread, our main program. So if there's no root, we want to just get out of this program, right? So I'm going to say if there's no root, then we just want to return current path being explored. Now the first thing we want to do is to establish which path is being explored. Right now we're just at the root. All right, so I want to push this number, in which case it's 5, to this current path being explored just so that we can keep track. So all you got to do is write paths that add up to sum. Let's just copy and paste that. And then we want to push the current root.val. Remember, we got val from this definition right here that Leetcode gave us. So the val is going to give us 5, 4, 8, blah, blah, blah. All right. And as an instruction, again, we're just adding current node's value to the paths that add up to sum. Just keeping in some instructions going right here. So once that's been added, so now if we had an array of paths that add up to sum, it would look like this. So it would just have a 5 in there, and it would be blank. So now we want to check if we have found a path. So this is our first pass, so we have not found a path, obviously. But maybe we'd be on this 2 down here, and we would have found a path, right? 5, 4, 11, and 2. So how can we check that? So we want to say if there's no root left, and that satisfies this equation right here. A leaf is a node with no children, so we need to make sure it has no children. So if there's no root left, and there's no root right, which would mean that it doesn't have any children. So in this case, like 1 has no children, so that's good. And the root.value equals our sum. And I'll show you how this works in a minute with our recursive call. So if all of these add up and check out, then we want to take the current path that's being explored. So we got all the way down to this 5 and said, hey, this path adds up to 22. So we want to take this current path being explored. So let's copy that. And then we want to push that to our solutions array, paths that add up to sum. So let's paste that right there. And then of course we also want to slice it so that we're creating different arrays. So that's a JavaScript method. And essentially what this means is that we found a path that works. Now, if we haven't found this, right? So if we're on 8, the program's going to say if not root.left, but there is a root.left. So it's going to skip this block entirely and go to the next one. Here's where we want to use our recursion. And recursion just passes all this information up to this top function right here and sends it back down again. So it's kind of like going on a loop, all right? And in this case, it is our base case is right here. You always want to have a base case when you're working with a recursive function so it knows when to stop. Otherwise, you've got an infinite loop. So the final thing we've got to call is all we've got to do is just copy this and run it down the left side and then run it down the right side of the tree. And then we just need to change a couple of things. So since we're going down the left side of the tree, we want to take the root. Remember, right now we're at 5. We want to go down the left side. So that means right down here, we want to go down the right side. And then we don't return the exact sum because each time we go down a node, the sum gets smaller, right? If we're looking for 22 and we subtract 5, then we're left with 17. So 8's not looking to equal, so the rest of this path is not looking to equal to 22, it's 17. So we're going to say sum minus root.value. In this case, 22 minus 5 is what we're going to be looking for in the rest of this path of 8, 4, and 5. And then the rest of this stays the same. And then finally down here, we also want to do the same thing. Root sum minus root.value. Cool, so once these have been passed down, the final 2 steps we want to do is we want to take the paths that add up to sum, because by this time they've all been recursed through, so we want to take the paths that add up to sum. I'm just going to copy and paste that and make sure I don't misspell it. And we want to pop that off of our stack. So essentially this shoots us back up the recursion tree. All right, think of a recursion tree as a spring-loaded tension rod that each time you take it down a recursive function, it kind of tightens up. And then when you get to the base case, the bottom, it shoots all the answers back up the recursion tree, and it pops out your answer at the end. And then, of course, finally, you just want to return the current path being explored because that will add to our answer. And then at the very end, we, of course, want to change this answer to our actual function name, and then we want to pass it the root, the sum, and then those 2 arrays that we created up above, if I could type. So let's run this one more time just to make sure it works. All right, and it does with a runtime of 88 milliseconds, so not bad. So that is how you solve the path sum to Amazon problem that's going around. It's a recursive depth first search function, and you're just traversing the tree. Most of the time when you're working with recursion, you're just changing 2 of the variables right here. So in this case, root.left, and then sum minus root.val, and then passing everything else that you did in the first time. Hopefully that was helpful and made things a little bit clearer. Let me know in the comments if you do have any questions. Please subscribe to the channel if that was helpful, and I'll see you next time.